Hi everyone, I'm Dacia Cipher and I'm going to review power analysis using the 7 most common effect sizes, and we will go through exercises using the free software called G-Power. Hopefully you have already read exercise 24 in your Grove and Cipher workbook, and you're aware of the 7 most common effect sizes. Those are the Pearson R, the R squared for multiple linear regression, Cohen's D, Cohen's DZ for paired samples, Cohen's F for ANOVA, uh, D, which is difference between rates, and the odds ratio. We're going to review those today. So I have G-Power downloaded and pulled up on my screen, and we're going to go through some examples. Now here in table 25.1, you can see the 7 most common effect sizes divided into 3 categories: what Cohen considered small effects, moderate effects, and large effects. So these are just adjectives, they're guidelines. Cohen wrote a seminal book in 1988 that reviewed these 7 effect sizes and cut them into these 3 categories based on his research and his experience with statistical applications. So one of the most common effect sizes is called the Cohen's D. D is italicized to delineate it from just a lowercase d, which is just the difference between 2 rates. So in this first power analysis, the G-Power software is used to determine the required sample size based on a moderate anticipated effect size, the Cohen's D, which is, we'll use 0.5 based on the table, with an alpha of 0.05 and a power of 0.8. Now remember, power is a probability, and in most nursing research, our threshold is 80% for desired power, 80% or more, meaning that we are comfortable with an 80% or higher probability of detecting an effect if one actually exists, right? And so let's go through this. We open G-Power. We go to the t-test test family, means difference between 2 independent means. It's already set at a priori, meaning we're doing this power analysis before we actually perform the study. And we'll change tails to 2 tailed. Effect size is already at 0.5. Our alpha is already set to our desired alpha of 0.05, but our power we are going to change to 0.80. And I should note that I turned off, when you click on view, I am hiding the plot. The plot takes up too much space for me, so I am hiding the plot so you can see all of my screen. And that's it. Very simple. Click calculate. And if we were going to perform a study where our anticipated difference between the 2 means where it was moderate at 0.5, at alpha of 0.05, power 0.8, meaning beta of 0.2, we would need 128 total subjects to achieve those parameters. So I will stop here and just remind you that, as I noted in exercise 24, identifying an anticipated effect size is the most difficult part of a power analysis. It's just the most trouble. You have to do so much work to identify what has been reported in the prior literature. And if it has been reported, where do you find those means and standard deviations needed to actually know what to put in this cell? That is actually the hardest part. You have to do such a thorough literature review. Sometimes you come up short. You can't find any prior published literature that is reporting what you are investigating. And then it's time for other lines of research, such as your own, planning a pilot study, or contacting investigators you know. It is very difficult. But I am going to give you a little example of how you might do that. I have here, I put in your this week's folder, this article, the Buzzy Study, the randomized study of using cold and vibration for pediatric cannulation. And these investigators use the Buzzy apparatus to assist kids with their IV procedure. And their hypotheses were that Buzzy reduces pain felt during cannulation. And the second hypothesis is Buzzy reduces anxiety felt. And they reported means and standard deviations. So let's say that you're a researcher who is wanting to also perform some research using Buzzy or something similar. There were some limitations to this study. It would have been better to perhaps test more of a sham control. Anyway, but that's beside the fact. But let's just say perhaps you're wanting to improve upon this study, right? Well, when you go to Table 2, you can see the means and standard deviations and the results, the analyses used to address Hypothesis 1 in terms of the differences between the groups in pain. And sure enough, in this study, use of the Buzzy resulted in lower, significantly lower pain levels. So how about we enter in the means and the standard deviations and take a look at how many subjects we would need for our study if we were planning on examining pain between Buzzy and, let's say, a sham control, maybe a better, more refined control. So what we do is we go to G-Power, okay, and we are going to click on Determine. Let's determine the effect size. And you see to the right, a little window pops open where you can enter means for group 1 and 2, and then the standard deviations. Well, let's enter the means for pain. Well, I can't. I'm going to have to just go back and forth. Whoops. Okay, so what you see here is I've entered the two means for the Buzzy and the control group for pain and the two standard deviations. And then I'm going to click on Calculate, and then Calculate and Transfer to Main window. And then what you see here is the actual Cohen's d value was almost 0.98. So as you know from our table in the book, that is considered a large effect, a large difference between the two groups. So from there, let's say that our other parameters we'd like to keep the same, click Calculate. So if we were going to we were going to conduct a future study with this amount of separation in the two groups and anticipate in pain, that we would anticipate, it would be only 36 total subjects needed, 18 in each group. Okay, so you can do the same thing for anxiety. You can move on down to the next table. And then as you can see, the Buzzy anxiety levels, and you can enter in the same thing here. So you can go to .94 to 0.9, 4, and then 106, 139 here, 1.06, 1.39. Calculate and transfer to main window. That's also a very large effect size at 0.93. Click Calculate, and you would need 40 total participants to conduct a study with this level of anticipated difference in anxiety between the groups. So that's how you do that. That's how you would extract information from a published article and perform a power analysis with it. Okay, let's move on to the next example. Here is a Cohen's F. Now we would use a Cohen's F in our power analysis when our anticipated effect size is going to has to do with some kind of analysis of variance. It could be a one-way ANOVA. It could be a different kind of a ANOVA, such as a mixed factorial ANOVA, but is some sort of ANOVA. So this example performs a power analysis with a small anticipated effect size of f of 0.1, with our alpha and power being the same. So now we would go to our test family of F tests, and then we will select our ANOVA fixed effects omnibus. We'll move our F, we'll change the F, anticipated F to 0.1, and move our change our power to 0.8. And then I believe the number of groups is 3. So we need to change 5 to 3. Click Calculate. And for a small anticipated F, Cohen's F, we are going to need 969 subjects because, as you've probably figured out by now, a small anticipated effect is going to require a lot more subjects to demonstrate significance. Okay. And sure enough, on page 284, you see that we performed it correctly with a total sample size here required 969. So how would you write that? Well, you would write it here on the next page, something like 969 total participants are required, 323 in each group, because we're using 3 groups to test a hypothesis using a 3-group one-way ANOVA based on a Cohen's F of 0.10, alpha equals 0.05, power equals 0.8. Just one sentence will do it if you need to write this for an article or a thesis or dissertation. All right, next up is the Pearson R. So oftentimes we have effect sizes that aren't actually statistical procedures. So you note that a Cohen's F is calculated from means generated from an analysis of variance, right? Or a Cohen's D is generated from means and standard deviations from a 2-group design. But here, the Pearson R statistic is its own effect size. We don't take that and then turn it into something else like we did for the first 2 power analyses. The Pearson R is the effect size, so that makes it easy. So what are we doing here? We're using a large anticipated effect of R for our next power analysis, same alpha and power. So let's go to exact, and then we'll pull down to correlation bivariate normal, and then 2-tailed, a large correlation of 0.5, change your power to 8, and the null correlation is 0. So the null hypothesis is there is no correlation, so we set that the same. So from there, click on Calculate. How many subjects do we need? We will need only 29, right? As shown in the figure, 29 total participants are required to test a study hypothesis with an anticipated R of 0.5, right? Because 0.5 is a large effect. And as I noted earlier, a large anticipated effect will require many fewer participants in your study, and a small effect is going to require many more. So a small effect doesn't indicate that there is no association or no effect. It means it's real, but it means it's real small. Okay. All right. Next up, next power analysis is our friend, the R squared for linear regression. Now, the R squared is generated from any output, statistical output that you generate when you're performing a linear regression analysis. And this power analysis is going to use an anticipated moderate R square of 0.15. Same alpha, same power. So this time you go to G power and you select F tests from the test family. And then from F tests, you select your linear multiple regression fixed model R squared deviation from 0. Let's take a look. F. Here it is. Deviation from 0. I'm moving that. Okay. The effect size is already set here. So this is what we have to do. We have to determine from the R squared what we have to do. Let me show you your window here. Okay, when you enter the hypothesized effect, you have to enter it into that determine window and make your window look just like the one. Well, the box isn't shown, so I'll just do it for you. So you change that to 0.15, calculate and transfer over. So an R square of 0.15 translates into an F squared here, what is being used in the math actually, as 0.17. The F and the R squared are cousins because an analysis of variance and linear regression are very close. They're like first cousins, so it's all related. Move your power to 0.8, and how many predictors are we having here? 3. So we're going to change 2 to 3. Click calculate. And G-Power tells us that with anticipated R square of 0.15, which is a moderate R squared, we will need 66 participants to perform the study. And sure enough, our book tells us the same, right? Next up, power analysis 5, the odds ratio. Now this is a tricky one because there are a lot more choices in G-Power, but I do the steps where it's pretty straightforward and you can't really go wrong even if you vary your parameters a little bit. It's still good. You'll still get pretty much the same thing. The thing about odds ratios is sometimes you're computing an odds ratio with 2 binary variables, right? So in epidemiology, we have odds ratios from case control studies where we have a disease group and a non-disease group, and we have an outcome that's binary. And so you can generate an odds ratio to indicate the odds of improvement or response in a binary way. And so we can easily do that here, and that's what we'll do for this power analysis. But you can also do the same thing. You also have odds ratios as a very important part of logistic regression, and we're going to be covering logistic regression in the next month. And so that's why this 5th power analysis is so important, is that if you're simply planning one single odds ratio as your planned analysis for your study, or you're planning to actually perform logistic regression, this is where you go in G-Power to perform your power analysis. So we are going to use an anticipated small odds ratio of 1.5, same alpha, same power. So this time you'll select the test family Z tests and then select logistic regression from the statistical test. Even if you're not planning to perform logistic regression, that's what you're going to need to choose to perform a power analysis that's going to use an odds ratio. Okay. And then you want to be sure you do these steps in order and make sure each parameter is set to just how I listed here in exercise 25 so that you can get the same results as I did here, right? Okay, so we'll go to test family exact. Oops, that's not test family exact. It's z-tests. Test family Z, then logistic regression. Okay, two-tailed, always two-tailed. Our anticipated odds ratio is 1.5. We're going to change this, the probability that y is 1 when x is 1. So the probability that your dependent variable is 1 when your predictor is 1 is going to be 0.3, not 0.2. Your power is going to be 0.8, not 0.95. Okay, and then the x distribution is binomial, and we'll leave everything else the same. Okay, and then click on calculate. And as you can see, we will require 853 participants that are going to be needed to have a small anticipated odds ratio of 1.5. So again, small effect sizes are going to drive your sample sizes being much, much higher. All right. Okay, 6 power analysis is the D difference between rates or proportions or percentages, right? So this is when you are comparing two completely different groups on some binomial variable so that you have a percentage. So we have an example where we're going to perform a power analysis with a large anticipated difference in rates. So 25% difference between rates here. And now we're going to go to the test family exact. Okay. And this is based on a Fisher's exact test. So we're going to go to exact. And go down to 2 independent groups, Fisher's exact test, always two-tailed. Proportion 1 is going to be left at 0.5, but proportion 2 is going to be set to 0.25 to represent a 25% difference. Now you could have put 0.25 here and 0.5 there, but for ease of saving time, we'll just do it like this, but you'll get the same result if they're switched. Make sure your power is 0.8. Click calculate. So for a large difference between rates, we'll need 128 total participants for a large anticipated effect size, right? And there we go, 64 in each group to test the study hypothesis using a Fisher's exact test. Large D, alpha of 0.05, power of 0.8. There you go. And then for our last power analysis, the Cohen's DZ. Now this is only used for paired data, such as a paired samples d-test. So this last power analysis is focusing on a single sample. You have one sample assessed multiple times, so repeated measures. Specifically, this is for two pairs. So a group of people assessed twice only. And when the correlation between those two assessments is about 0.5, the magnitude of the difference stays the same as with Cohen's D, where 0.2 is small, 0.5 is moderate, and 0.8 is large. So we'll go to our test family t-tests. Test family t-tests. And this time we'll go to means, difference between two dependent means, right? and then to always two-tailed. And we are using a small anticipated effect size for this example. And then power is 0.8, alpha is 0.05. Click on calculate. So for a small anticipated effect for paired samples, we will need 199 participants. Right? Just like that. So, so here's something, a little fun exercise for using, doing a power analysis for paired samples. This study is a single sample study of aspartame consumption, where there are washout periods among this this cohort of participants. The researchers looked at the effects of various outcomes of aspartame when subjects are made to eat large quantities of aspartame in their diet. And the outcomes were mood, depression, and cognitive tests. And the researchers report the necessary tables so that you can we have means, we have standard deviations, so that we can take a look here at what the researchers found. But that's not what I'm looking at here. I highlighted this part here on page 3. The researchers actually reported their power analysis results. And they write, with a statistical power of 0.8, alpha of 0.05, an effect size of 0.3, with a planned medium effect, an estimated sample size of 30 participants who would receive both treatments was calculated, because these folks consumed very differing diets. One diet didn't have aspartame, and then the washout period, and then they did. So it was a crossover study. They ended up enrolling 30, and then ended up with complete data for 28. But they did find a mix of results. Some of their results were not significant. So let's replicate their power analysis and let's see what we find. Let's take a look. So when we entered an effect size of 0.3, and we have the same alpha and power parameters as listed here, we click calculate. Take a look-see. The required number of people is not 30, it's 90. So these researchers made a mistake. They only enrolled 30 subjects when in fact they needed at least 90. And so the unfortunate thing about making a mistake with a power analysis is it could cost you a study. If you take a look at some of these results here, you do have trends and differences with neurobehavioral scores, but for working memory, the paired t-test, it wasn't enough. With only 30 people, the difference was not significant here for working memory. But you can see that the working memory group had lower scores in the high aspartame. When the group underwent the high aspartame diet, their memory was lower than when they underwent the low aspartame diet. And this would have been significant had they enrolled more subjects. So that's a shame. And so power analysis is so important because your funding, your entire study results can be dependent on this enrollment decision. So I thought it would be really important to share with you. And both of these articles are available on Canvas so that you can see for yourself. So the next step that I would recommend is in exercise 25, going through each of these study questions in exercise 25, perform the power analyses, and don't look at the answers. Perform the power analyses and then check your work in starting on page 296, where you can see the G-Power results for each of the questions. And I think after the end of those study questions, if your answers match those in the book, I think you're in really good shape to be way far ahead of most people in this world in terms of how to do power analysis. Okay, thanks for watching. Hope this helps.